and welcome to the Day 6 Session 12 of ATAL Online FDP on Quantum Intelligence, Integrating Quantum Technology with AI and ML. The speaker of this session is Dr. Amit Shah, and the title of his presentation is Learning the Noise Through Verification for Quantum Benchmarking. Dr. Amit Shah is a postdoctoral researcher at INRA Paris and research staff at École Normale Supérieure PSL University. He previously worked as a consultant and scientific expert at ABN and was a CSIR senior research fellow. He holds a PhD in information technology from the University of Calcutta. His research in quantum computing focuses on quantum algorithms, multi-valued logic, circuit synthesis, and verification. Dr. Shah has an extensive publication record with more than 19 journal articles, 9 conference papers, and 2 patented inventions. He has delivered more than 20 invited talks and workshops at international conferences and institutions, including IEEE International System on Chip Conference and workshops at CDAC and NIT Raukalla. An active contributor to the academic community, Dr. Shah serves as a reviewer for leading journals and conferences. He is also proficient in quantum software tools, including QSkit, Pennylen, and Kill. May I request Dr. Shah to start his session, please?
Yeah, thank you, madam, for the kind introduction, and thank you for inviting me on this platform so that I could discuss about my work, or rather quantum computing. Uh, I have already seen the lectures, like the topics. I think the basics of quantum computing have already been covered by various eminent speakers, and I'll try to focus on more on noise characterization that I told on my title, noise characterization, verification, and benchmarking. Okay, let me share my screen first. Yeah. Is it visible? My slides are visible, right?
Yes, it is visible. Kindly give in the
Okay.
slideshow mode.
Yeah, sure. Yes. So, so today I'm going to talk about estimating the noise or learning the noise through verification for quantum benchmarking. So before starting my presentation, these three terms, like estimating the noise, verification of a quantum computation, and quantum benchmarking. So these three terms I'll be going to use more often, and these terms are very similar. They are very interrelated. But from today's talk, my aim would be differentiate between these three terms. Like after completion my talk, you will be understanding that this estimating the noise is a different from verification and benchmarking, and also this verification is different from the quantum benchmarking. These three terms are like individual entities. So before going into the details of my talk, let me introduce my team. I am currently based in Paris. I am associated with INRIA and ENS. It is already been told by ma'am. This is like a medium-sized group, and we are there are many physicists, mathematicians, and some computer scientists also, and we are working on various topics like continuous variable, discrete variables, and like error correction, like verification that I'm going to talk about today. Um, and apart from that, I want to acknowledge my collaborators. Since I'm going to present one of our works also, I want to acknowledge Sorbonne University and University of Edinburgh. And yes, so this is the overview of my talk, and I'll start with the basics of quantum computing, not in the details, because I have seen that it is already been covered in past 5 or 6 days. So I'm going to more talk about the motivation behind my work, because why is it needed? This should be addressed first, what I believe in every presentation. So I'm going to motivate you before going into the details of my work. So I'm going to talk about three different eras first. Like I'll start with the NISQ era. What is the current quantum era, right? Like the noisy intermediate scale quantum era. And next, I'll talk about something about early error correction era and fault tolerant quantum computing era. And after that, I'll talk about little bit qubits, which is beyond qubits, like what is like since since uh, since the quantum computation can be a high dimensional quantum system, so what we could find beyond the qubits. And why I do like this qubits, because for the last 9 or 10 years, whatever I have worked on quantum computation, I have emphasized my work on this high dimensional quantum system. So I would love to tell about something about qubits. Next, I'll go through the main topics of today's talks, which will be started from benchmarking of a quantum device, how it is like related to verification, how we can estimate error through verification for benchmarking. So I'll talk about these three things, and I'll try my best to separate these three things, so that after this talk you can understand that these three are not similar, these three are not same, these three have some distinct matrices to identify them individually, right? And finally, I'll talk about our recent work, which is not yet finished, but I would like to talk about this work, since this is a very exciting work that have been done by various European entities, and I'll showcase our work. Yeah, and finally, I'll conclude some future directions, and I'll conclude with some like future direction. Yes, let's start. Yeah. So let's start with the quantum computation part. So I think you have already understood that quantum computing is kind of different from classical computing, and how it is different from classical computing, because it utilizes qubits, which like qubits, classical computation doesn't have qubits, right? It has normal classical bits which can store 0 or 1, but qubit can store 0 and 1 at the same time with some probability. So that can be used for our algorithmic approaches, right? Apart from qubits, there are two more important things. One, mechanical properties, quantum mechanical properties, superposition, in which, like, I can give an example of coin. Like if you toss a coin, you don't know the outcome of that coin, so it is either head or tail. So it is in a superposition. So it is in a superposed. It is a superposed coin, right? If you measure it, then only you will get the outcome of it. Either it would be head or it would be tail, right? And the next thing is entanglement. Entanglement is like how two qubits are correlated, right? How they are correlated, like they can be correlated in such a way so that you can, if you change one of the qubits, the other will act accordingly, right? So these are the two quantum mechanical properties that can help to differentiate quantum computation from the classical computation. And it has some extraordinary properties which can help to solve the complex computational problems in such a way so that we can get the asymptotic advantages, right? So what are the advantages, like what are the algorithms have already been proposed by the different scientists? So maybe I can speak like 5 or 10 quantum algorithms, but before that I have to start with the two algorithms. One is Shor algorithm, which is very famous, which is proposed in 1993 by Professor Peter Shor from MIT, and it Shor showed that an exponential time problem or NP problem can be solved in a polynomial time, right? So the factoring problem can be solved very easily with a scalable quantum computer, but and at and it can break the RSA crypto system, and it's fascinating, right? An algorithm can break RSA crypto system in polynomial time, and that is huge, right? And later on in 1996, Lob Grover came up with Grover search algorithm, and it was not it was not had it was not having super polynomial speed up, but it had quadratic speed up. That means if you search unstructured database in classical domain, it takes at least at most n number of searches. But Grover showed in his algorithm that it can be achieved in root over of n times, right? So these are the two main algorithmic approaches proposed in 90s, which gave us the enough motivation to work on the quantum computations. So after that, there are many algorithms. I can say like HHL algorithm or QAOA algorithm or other algorithm came up, but or like quantum walks for binary ordered tree. So these are the famous algorithms came after these two's invention, but and those also are very promising for different complex computational problems, and it has several applications. Like I have mentioned some. It can be used in cryptography, like breaking RSA or secure communication with quantum key distribution, or for optimization, because you know that industry or government, different government from different countries are investing billion dollars. Why? Because it this quantum computation can be helpful for optimization problem. What type of optimization problem? Any optimization problem, like supply chain management. So that is why Amazon is investing so much money, like logistics, AI ML model tuning. So every optimization problem you can choose, you will get a benefit if you are using quantum computation or quantum algorithms, right? Another main thing is drug discovery. So yeah, just 5 years back in 2020, it was a COVID. It was COVID situation, right? And we were out of drugs. So yeah, drug discovery and the life science related or chemical molecular simulation. Uh, these are the things need to be addressed very soon, right? And this is the need of the hour. So quantum computers or the quantum computing, quantum algorithms can give some boost to develop algorithms to obtain this to get the to discover these drugs or to simulate these molecules, right? So So this is the introduction of quantum computing from my side. I'm not going into the details like Blosphere or like quantum gates or something like that, because I believe this already been covered. And one more thing I want to tell you, if anyone has any question at any given time, you just can ask me, right? Because I love to do interactive session. Uh, as compared to just I'm saying, and after that you are going to ask. You can stop me anytime and you can ask me anytime. I would love to give you answer. Okay. So this is one QC timeline I want to show you. I have taken this image from Q Control, which is a international company on quantum computing. So yes, so this is the niche era we are currently having, where the hardwares are very noisy, and we need to deal with the noise. We don't have many qubits so that we can correct the errors, because for error correction you need so many qubits, and but we don't have much qubits. People are working, I believe. The previous talk was given by Ritojit, I guess. He is very good friend of mine. He's from IBM. He's also my collaborator. So they are they are coming with different hardwares, and they are trying to increase the number of qubits, like IBM. Every other entities are trying to do so, but still we are in the niche era, so we have to deal with the noise, and we are not getting the actual quantum advantage because of this noise, right? Because the hardwares are very noisy and you are not getting the good results from a computation. But things will be changed very soon, I believe, because after this niche era, there will be like early quantum error correction era, where quantum error correction will be a main topic in quantum computation. So I want to tell you everyone that just go beyond like quantum circuit synthesis or algorithm. You just try to learn quantum error correction also, because that is going to be the future of this quantum roadmap, right? So next era, and after that, down the line, 5 years or 10 years, we'll get the actual quantum advantage, right, from different computational problems. And finally we'll be having FTQC era, that is fault tolerant quantum computation era, where we will have like billion of qubits in a quantum hardware, and you can easily implement the complex problems with very short runtime complexity. And like you can see that I have shown an image where like 20 years of roadmap has been shown, but I believe this FTQC can be achieved in like within 15 years or so, because people are investing so much money and people are working on quantum computing unanimously, right? So I have already like covered this slide, because huge promise of quantum computing, but miles to go. Yes, I have shown that it's you need 10 to 15 years more, as per my understanding of quantum computation. I might be wrong, because maybe in 5 years there will be a fault-tolerant quantum computer. I'd be the most happiest person if it happens, right? But I believe there is some time to be there, and we have enough time to learn quantum computing, quantum algorithms, and other stuff related to quantum. Yeah. So we are in the niche era, and quantum computers are very small, because it has like this small number of qubits, and the computers are very noisy. Whatever you are doing in computation, you are getting noisy results, right? So we have to go for miles to achieve a good result. So So quantum noise. So I am saying very often this term quantum noise because yes, everything is noisy in quantum computer right now. I hope Ritojit also told the same thing. I believe because he also works on noise and yes, like there are different type of noise in quantum computers and and because of various reasons, not only not there is not only a specific reason to having noise in quantum hardwares. There are like various reasons. Like I have taken this picture from Qiskit and like you can see that you can have poor calibration as IBM is working on superconducting qubits, they have to calibrate their qubits for this poor calibration reasons. The qubit can be noisy. Like state preparation, you need to prepare your state in such a way so that the noise becomes low, but it really difficult to do so. So like measurement errors, one of the errors, right? Decoherence, incoherent noise, leakage, crosstalk. So maybe there are so many type of errors, and for that reason you cannot have a good result from your computation. So we need to deal with this sorry, hello. Yes. Okay. So there are like several type of noises in quantum hardware, and uh, that making us so difficult. That making us our life so difficult to get a quantum advantage or quantum supremacy, right? So in this niche era, like I mentioned that we need to run larger circuits, right? Because you need to your algorithm or your computational problem should be huge, right? An easy computational problem can be solved in classical computers. You don't need a quantum computer. But whenever you are targeting a complex computational problem, you need to design your computation. You need to solve your computational problems through a quantum algorithm, and for that reason, you will have a quantum circuit. And your quantum circuit will have like various various qubits, number of quantum gates, so your depth of the circuit will be huge, right? So you need to run your larger circuit on a small quantum computer in current NIST quantum computer. And for that reason, we have worked on the circuit cutting theory. And through that, we can like cut the circuits, we can cut the circuit through gate cutting, through qubit cutting, and we can and through that we can implement the small sub-circuit in a small quantum computers, and we can implement those small circuits on different quantum hardwares, and you can get the result for a larger computation. So why I am showing this circuit cutting in my verification or noise characterization or benchmarking PPT, because I love to work on circuit cutting, and it is one of the topics that is very popular in current niche era. So first of all, I'm trying to give you some motivation of quantum computation of today's era and tomorrow's era, so that you get enough motivation to pursue to understand the quantum verification and other things, right? That is why I'm showing some of the topics that I am interested in, and I am currently working on these topics. So this is the circuit cutting thing, and we are working on like finding cut location. A good cut location is very much needed so that the classical post processing cost can be reduced, right? So in this way you can implement a larger computation on small quantum computer, but with lots of classical overhead, right? So for that, you have some limitation to do the circuit cutting also. And through the circuit cutting, we achieve some noise reduction also in a quantum computation, because whenever you are cutting the circuit into small sub-circuits, it becomes small, it has less number of qubits, it has less number of gates, and it can be implemented with less number of noise also, because you are having less number of qubits and less number of gates, right? So this is the Niskera I wanted to show you, where we are currently working on circuit cutting. Next, I want to show one more slide on this current from this current Niskera, and that is the paper from IBM last year, I guess. Yes, last year December, I guess. And they have shown that you can combine this small quantum processor with classical communication. So it's fascinating, right? Like 10 years back when I started, like 9 or 10 years back when I started my journey in quantum computing, there was no quantum computer. Right? We used to simulate our models in MATLAB, because on that time there was no quantum computation, no quantum computers. Very few people were working on quantum computation, quantum information in India. But after this 9 or 10 years, the things have been changed rapidly, right? Uh, Not only they have come with various quantum computers, now they are like integrating different processors, and they are trying to connect them, and they are trying to interconnect them, and they are trying to making them a single processor by connecting them. And we know that combining this classical this quantum processors, you need some entanglement between them, you need some communication channel. But it was IBM who showed that you can do with some classical communication also. So it's fascinating. Like you you can do multiprocessing on quantum computers also, right? So these are the motivations which help you to pursue a complex topic like quantum computation. Well, next I'll talk about little about early quantum error correction era and MTQC. Like, we know some of the error correcting code; those are very famous. Like, I'm not going into the details because I'm here to give you like abstract view of this thing, so that you could get enough motivation for your future in quantum computation. So there are like many error correcting code, and you need this error correcting code, right? Because otherwise you cannot have good result from your computation. You need to do error correction because the noise is very colossal, and you need to eradicate those noise from your computation. And error correction would be the best thing for your good computation results. And here are some examples of error correcting code. I'll start with the Steam code, Shor code, Bacon Shor code, concatenated code, color code, Boston. Like many error correcting codes are like proposed by the different various scientists, and people are working on this code, and they are trying to show what would be the resource estimation for a different complex computational problems using this error correction code, so that whenever the larger quantum computer will come in the market, you can implement your circuit as per the resource estimation, right? Next is I'll talk about another code, that is LTPC code, which is like talked about by the IBM's paper, another Nature paper from 2024, and they showed that the good time is coming very soon with in error correction and fault tolerant error. They have shown that that you don't need like you if you are using surface code, you need many physical qubits. But if you use LDPC code, they have shown through example that you need low overhead for a fault tolerant quantum memory. Then after that, Google, because they are using the surface code very often, they came up with another Nature paper, and there was a little fight and this is competitive, very much competitive and healthy fight, right? Because it's I mean, these fights are helping our society, because they are giving better and better results in error correction. And if the hardware team can come up with very large quantum computer, these results will help us to have the good results from some complex computation. And as a computer scientist, I am more focused on the computational problems, because we are the one who are going to solve these computational problems through quantum algorithms, and we need to design the circuits, and we need to implement them on a real hardware. So they also showed that through surface code we can go beyond the threshold. Like there are different thresholds for this quantum errors, and you can go beyond this threshold using this surface code, right? So this is the last slide regarding the fault tolerant error, and I think I have given already enough motivation for this NISC error correction era, and fault tolerant era. Now I want to take another 2 or 3 minutes to discuss about QDIT, because I like QDIT. So QDIT is like beyond qubit system. I think all the talks you have been given for last 5 days, everyone has talked about qubits, right? Simple qubits. But inherently, these quantum systems are multi-valued, right? What does it mean? It means that it has not only 0 or 1, it can have like 0, 1, 2, and any finite dimensional system. It can have d-dimensional systems also, right? What is the advantage of this d-dimensional system? It can have larger state space, right? If you take ternary system like 0, 1, 2, then you can have like with 2 qubit, you can have like 4 states, right? With 2 qubit, you can have 4 states, 2 to the power 2, that is 4. Now, if you take 3 qubits, that means you are taking 3 ternary quantum bits, right? Then you will have 3 square number of states. That means with 2 qubits, you can have 9 number of states. So the largest state space you can get from these qubits. It also reduces the circuit complexity. My whole PhD is all about reducing the circuit complexity with this QD. So yeah, and currently I'm trying to implement those QD related works on a QD related platforms, like for validation. So it's very fascinating for me that finally I'm trying to implement my PhD works on a quantum hardware, QD quantum hardware. Yeah. So what does it mean by reducing the circuit complexity? It gives the efficiency of quantum algorithms. It's very, very obvious and very trivial, right? Because if you reduce the complexity of your circuit, your runtime complexity automatically been reduced, right? So your quantum algorithms will automatically been efficient by using this QD, right? But the disadvantage is again that bad thing, that noise is like hampering every possible good thing in our lives, right? So whenever you go beyond qubit, the noise becomes more colossal. Yeah. Okay. Sorry, is there any question?
আমাদের হাতে কিছু ইয়ে হবে না, কারণ আমরা বাড়িতেও যেমন মানে কোনো জিনিস ফিরে রাখি না। হচ্ছে ইয়ে ওদের সবসময় বলতে হবে যে দোকানের সময় তো তাড়াহুড়ো নেই।
হ্যাঁ, ওদের নিয়েই চিন্তা সব। আবার 5টা থেকে 5:30 শেষ। হ্যাঁ হ্যাঁ, ইয়েটা 3টে শেষ হয়েছে।
Hello,
শেষ হলে হয়নি।
hello.
Hello.
Yeah,
Hello.
am I audible?
You are audible, sir. But I would
Yeah.
like to request all the participants to keep their microphone in mute mode. The session is going on. While you are talking, you please keep your microphone in mute mode, please. Sir, please continue.
Thank you. Yeah. Okay. So finally, I want to give you some glimpse of intermediate QDIT. So I worked on this intermediate QDITs during my PhD, and it is like you can have some hybrid quantum systems in your computation. Like you can have qubits, you can have qubits, you can have q-quarks, like a d-dimensional system you can have. And we showed that through this intermediate qubit thing, you can reduce the complexity of your circuit. You can do decomposition of multi-control Toffoli gate with logarithmic depth. So yeah. So these are the motivation I wanted to give you all, like starting with the NIST, what we are currently doing, like circuit cutting is one of them. Next is early error correction era, fault tolerant era. We are trying to show the fault tolerant implementation of this hybrid quantum gates also, and beyond qubit system, like there is beyond qubit system also, and that is QDIT. Okay, so till this introduction of quantum computation and beyond, if you have any question, I would love to answer if you have any question.
Hello, sir.
Yeah.
Sir, what do you mean by intermediate qubit, sir?
Yeah, so intermediate QDIT is like, okay, intermediate QDIT is like, suppose you have a circuit, right? You have a circuit with only qubits, right? You have a circuit with only qubits, and all the gates are qubit gates, right? Or binary gates, right? Now you can do one thing, that is like you are initializing your qubit with any initial state, right? And in the mid of the qubit operation, you can increase the energy level of that binary system to higher dimensional system. Why is it fascinating? Because you can do that. Like inherently your system is higher dimensional system. You are trying to control your energy in the system so that you can make them a binary quantum system. So after having a binary computation, you can uh, you you can go to beyond qubit or binary qubits to a high dimensional quantum system for a sake of time, so that you can do some computation with higher larger states with high dimensional quantum system, and again you can come back to the qubit system while you are measuring the overall computation. So for the intermediate of time, you can go to a higher dimensional system for your computation, and you are getting all the advantage of it. And after that, you are measuring the same qubit for the qubit system. That is why it is
So
intermediate.
give one example. Sir. Give one example.
Yeah.
Suppose if I initialize qubits with 0,
Yes.
and if I had adamant gate, and then one more adamant gate, it will give the superposition. If I measure, I will get
Yes.
any one of the values, either 1 or 0. So in that case,
Yes.
what do you mean by intermediate? Hello, have you understood my
Yes.
question?
So suppose yes, yeah. I understood your question. So suppose you have a circuit. Do you know Toffoli gate? Hello.
Hello, yes, sir.
Yeah. Yeah, can you hear me?
Yeah.
So suppose you have you have a Toffoli gate, right? So it has two
Okay.
controls, one target, right? And your
Yes.
controls are Hadamard, like you have said that you have taken Hadamard gate. So you have taken two Hadamard gates on the control, and you have a Toffoli gate, and these are like a fully qubit only system, right? So now
Yes.
these Hadamards are fine. You can decompose this Toffoli gate as and you have three number of qubits, right? You are only doing the high dimensional thing on the second qubit, right? You are making that particular qubit system for a sake of time to a qubit system, or 0 1 2 you'll have, right? So suppose you are initializing with 0, you are doing Hadamard, so you will have 0 and 1 combination of your qubit. Now you are applying some hybrid quantum gates like qubit gate, qubit gate with these with these two qubit and qubit, right? And you are like with 0 and 1, you can have 2 also, because you are making your qubit to a higher dimension system, that is qubit system, and you are utilizing that extra 2 information in such a way so that you don't need any ancilla to decompose your Toffoli gate. So in binary system, you might need ancilla gate, or you might need multiple number of T gate or C naught gate. But with the help of this intermediate qubit or intermediate qubit, like you are having not only 0 1 in your second qubit, you are having 0 1 2 value in your second qubit for a small amount of time, and you can compute that Toffoli with the help of 2 information, and you can do with three number of 2 qubit gates, and you can decompose that Toffoli, you can implement that Toffoli. So for the small amount of time, you are making that qubit system to qubit system, you are making that qubit system to qubit system, and you are taking the advantage of that particular 2 information.
Okay, sir. Thank you, sir.
Okay, thank you. Any other question? Okay, maybe I can move forward. So now I'm gonna talk about three different topics. One is benchmarking, because benchmarking is the main task like we have to do. Otherwise, like without benchmarking, you would not understand how powerful your computer is or how correct your computer is, right? So that is why benchmarking is required. And while I'm talking about benchmarking, I'm going to talk about noise estimation and verification also. And I'll connect all these three in the later part of my talk. Yeah. So let me start with the noise estimation. Okay. So why estimation the errors? Like why is it required? Like estimating the noise. So it is essential for improving quantum error correction and mitigation. It is obvious, right? Because you need to know about the error in your circuit or in your computation. Otherwise, how would you do the error correction or the mitigation? So that is why error estimation or noise estimation is required. And to predict algorithm performance, right? Yes, it's obvious also, because without knowing the knowledge of noise in your hardware or in your computation, you cannot predict the performance of your algorithm, right? So what are the metrics associated with this noise estimation? One is error rate. Like you need to know the error rate of every gate, every possible gate you have, and the noise channel, right? What type of a noise channel you are trying to characterize through this estimation of noise, right? So these are the things you need to take care in noise estimation. Here I'm going to talk about one randomized benchmarking thing, and don't puzzle with the with this benchmarking term, because this is not the benchmarking thing I want to show you. I'm gonna talk about benchmarking of a quantum hardware, and this is randomized benchmarking, which is been used for estimating the noise. This is not the thing for benchmarking a quantum hardware, right? So don't get confused, right? So what is randomized benchmarking? It's a technique to measure the yeah. Sorry. Can you come again? Yeah. So your audio is broken. Can you repeat once again? No, I'm not getting it. Maybe have you typed anything? No, you haven't typed it. I'm sorry, I'm not getting your question. Yeah, it's not clear.
Hello.
Yes.
Hello.
Maybe you can
Sir,
type it. Yeah, okay. Yes. So this randomized benchmarking, yes. So as I mentioned, that it tries to give some idea of the noise of a quantum gate in your computation, and also like it can give you the idea of the noisy quantum systems also. And yes, it is essential, because you need to have the idea of your quantum hardware, and it also helps to improve your quantum error correction schemes, because if you know the error, it would be helpful to use what type of error correcting code is required for your computation, and what would be the resource estimation for that computation. So randomized benchmarking does the estimation of noise part very well, and it is very popular also, right? So there are various type of randomized benchmarking. I have shown three type of here. One is interleaved randomized benchmarking, another is simultaneous randomized benchmarking, and another is like a cycle benchmarking. It can be used for various type of estimation of noise. So here is an example of doing randomized benchmarking. And again, remember, this randomized benchmarking is we are using for estimating the noise, not the benchmarking thing. Okay. So how randomized benchmarking works? So first of all, we need to generate some randomized gate sequences, and we have to apply into your quantum computation or quantum circuit. I hope something is covered by the previous speaker, because he was also talking about this noise thing and mitigation thing and something like that. So I believe this type of thing you have already been shown, because you are applying some extra gates there, so that you could estimate the error from your circuit. So what you are doing, you are applying some gates, and again you are applying some inverse gate for the mirror circuit, and you are trying to compare the output state to the expected state, because you have some expected results, and now you are giving some extra gates, and through that you are trying to comparing the expected state with the current state. And through the decay parameter, you can estimate the average error of your gate, and through that you can say that this is the error rate which I have for the particular gate in my system, right? Through that we can estimate the noise. So what are the advantages of randomized benchmarking? Like it's robust, because it doesn't affect for the like state preparation and measurement. It is scalable. It can be applicable for large scale quantum systems also. Uh, the, then it measures average error rate over the gate set. It can give you the overall view of your gate set, right? And but there are some limitations also, because it cannot estimate some complex noise like Markovian noise, right? And it always gives the average case scenario, like average gate fidelity. It always gives. So it doesn't provide the worst case performance. Okay. And you need to be very careful while implementing this randomized benchmarking, because there might be different type of gate sets, and uh, it doesn't work for the non-Clifford gates. Like, I believe you already know what is Clifford gates and non-Clifford gates. Clifford gates are like H gate, NOT gate, like these are the X gate. These are the gates are Clifford gates, and these can be classically very easily classically simulable, right? And because and there is another type of gate that is non-Clifford gate, and one of the examples of non-Clifford gate is T gate, and it is not easily classically simulable, right? That is why quantum computer is required. Otherwise, if T gate is also been simulated easily through classical computers, we might not need any quantum computer. And without T gate, you cannot have a universal gate set of your quantum computation. So that is why, it's unfortunate that with this randomized benchmarking, if you have T gate in your computation, it's really difficult to estimate the noise. Okay. Another approach of estimating the noise, it's ACES. I am very much familiar with this term, because my work is on this famous estimation technique of noise, and that is designed by Flemia back in 2021. And it is average circuit eigenvalue sampling, and it is kind of different from randomized benchmarking. What we are trying to do here, we are trying to estimate the eigenvalue of every gates which we have in our computation, right? And we do the eigenvalue sampling on Clifford gates, and yes, obviously it also works on the Clifford circuits. There is no proof that it will work good for the non-Clifford circuits also. And you can infer the Pauli, like, Pauli gates, right? XYZ. I believe it's already been covered. This XYZ Pauli error rates can be estimated from all the gates through this ACES mechanism. So I'm giving completely overview. If anyone is interested on this topic, you want to know more, you want to discuss, I am available for any discussion after that, because I have only 90 minutes to showcase these things, and to motivate you on these topics, because these are the topics are not very much discussed in India, because in fact 2 years back, when I was in India, I was not very familiar with these topics. But whatever I am learning in last 2 years, I'm trying to give the glimpses to all of you, so that you can have the idea that it's not limited to like quantum circuit, quantum gates, or something like that. People are working rigorously on different topics, and these are very important topics, and I think this is the right time for India to move beyond the simple implementation and simple things, because this is the right time to push our pedal so hard. Yeah. So that is why I am giving the overview. So if you have any question, any discussion, you can reach out to me. I would be love to, because I would love to talk about research related quantum computation. Okay, so this is one of the techniques apart from randomized benchmarking, and I have used this technique for our work also. and and uh, and like you need some number of circuits, because you need to sample them many times. You need to make some equation, some simple linear equation from those implementation, and if you solve those linear equations, you will have all the lambda value or the eigenvalue of of every gate. And it's very I mean it's very fascinating, right? Because through like we have worked on linear equations since we have started our uh, our science journey, right? And you are like creating some linear algebra by implementing these circuits many time, and you are sampling them many time, and you are making some equation, and you are solving those equation, and you can have the error estimation from the circuit. So so it handles both the like spatial and temporal correlation in noise. Like correlated noise also can also be estimated. I'll show that in the later slide. And it's like generalized framework that extends beyond traditional randomized benchmarking, right, with fewer restrictive assumptions. Because in case of randomized benchmarking, you need to restrict many things. But in ACES, if you have the key force circuit, you just take it and you are just do the statistical things, and you will have many number of equation. You solve them and you'll get all the information related to noise. So this is the noise estimation introduction I wanted to give you. Now I'll talk about I'm having only one slide on the definition of benchmarking. So this is the definition of benchmarking, and it is this slide I have taken from my postdoc supervisor's slide. And so why benchmarking? So I asked my supervisors on the first day that why are you so fascinating regarding benchmarking? So he's told me that like you need benchmarking, right? Whenever you go to buy your laptop or your PC, what do you check? Like you check something like RAM, something like processor, something. So there are different metrics. Now you are going to you have gone to buy a quantum computer. What you will check? You will check only qubits, number of qubits, or you will only check the number of you only check number of qubits? I think no, because maybe you have a 10,000 number of qubits, but if they are very noisy, it will not work, right? So you need a quantum computer which will have like a threshold, below threshold noise, and you can benchmark them in such a way so that a buyer can easily identify that yes, this is the quantum computer I need to run my computation, right? Whatever complicated problems I have, this quantum computer would be enough. This type of quantum computer would be enough to run my computation. I'm not going to buy a bigger quantum computer because I don't need it. I need this small quantum computer. And how will you get it? Because you know that someone has benchmarked that particular quantum computer in such a way so that you will understand that your application or your computational problem can be solved in this particular hardware. And for that reason, we have shown a benchmarking landscape where like component characterization control, like whatever I told in noise estimation or noise characterization or learning the noise. These are the three different terms, but they are like quite interrelated. Like learning the noise, you are trying to learn through some machine learning or something like that. Estimating some statistical thing you are doing, you are trying to estimating the noise. And noise characterization, like you are trying to characterize the noise. I mean, from where you are getting that noise. Like I have shown some noise noise. I have shown one noise related slide from Qiskit that was showing that there are several kind of noise. So through noise characterization, you can have the idea of where the noise is coming from, right? So this is the thing, and this would be very much visible in your quantum benchmark thing, because whenever you are going to buy a quantum computer, you will be knowledgeable enough to like what is the drawback of this quantum computer, like what is the noise sources I have, what is the estimation of that particular noise of a gate. So you will have all the idea. Then the system capability benchmarking, like this is the computational perspective. Like you have a benchmark where you can have the idea, like you have a problem, of I love cricket. So suppose you have a problem of selecting a team from different of a bunches of players, like Ajit Agarkar is selecting a team for the upcoming Asia Cup. How so it can be a computational problem, like it can be an optimization problem from 15, how you can select the best 11, how from 30, how you can select the best 15, right? You have different variables, you have different constraints, like you can pick only 2 wicket keepers, you can pick only 5 bowlers, you can pick only 7 batsmen, and they have some metrics, like you cannot rest out, like you need Bumrah, you need other bowlers. So it becomes a computational problem, and it becomes like NP hard problems, right? Because you need to have a best team in your hand. So to solve and is your quantum computer capable of solve this computational problem or not? You have to show through the benchmarking, right? Otherwise, how you would decide that this quantum computer can solve my problem? Okay. And next is the application utility verification, right? So now comes the point verification. So it is very important. Now I'm talking about noise estimation, noise learning, noise characterization, everything I have told. Like we have to deal with noise, we have to characterize, we have to estimate the noise. Again, I said that my quantum computer would be powerful enough to do this much of computation and everything I said. But how do you know that the computation that the computation will do the correct thing? Because you don't have a large quantum computer to verify the result, right? You don't have that particular quantum computer in your hand. Otherwise, you would solve with your quantum computer. You have gone to buy a quantum computer, and your computer has already estimated your computer already has the estimation of error. Your computer has your computer can do this complex computational task. That's okay. But if you don't know that either it is verified or not, what do you mean by the verification? It means that it is verified that it is giving me the correct answer. And that is from that point verification is coming. So verification is interrelated with this benchmarking. So we need some verification scheme where we can say that, yes, this computer has some noise issue. This computer can solve this algorithm, we can solve this computational problem, and we have also verified this with some scheme. So then the benchmarking is done, right? I hope you have understood, and you have understood the difference between noise estimation, benchmarking, and verification. I'll give some glimpses of verification now, because I have already mentioned that quantum verification is very much required. Otherwise, how would you know that your quantum computation is giving the correct answer, right? So, as per the definition, I have taken this from, I guess, ChatGPT. As per the definition of ChatGPT, the process of checking whether a quantum device or algorithm is producing correct results or not. Yes, I have already mentioned that. So I believe ChatGPT has given the correct result. Since quantum states collapse when measured, verification is typically statistical using repeated experiment. Yes, you have to. So you have to classically verify your computation, because you do not have larger quantum computer to verify your computation. You have some scheme with the classical verifier, so that it can be verified through that classical verification. Right. So why is it important? I think this example would blow your mind, because this is one of the examples of verification, that is cross entropy benchmarking, a method to compare the probability distribution generated by a quantum circuit against a theoretical ideal distribution. So it's a mechanism where you are trying to verify that your computation is good enough or your computation is correct or not. And through this cross entropy benchmarking, just mind this term, and you can Google it, or you can come up to me, and we can discuss on this cross entropy benchmarking also. Like, why is it fascinating? Because Google's 2019 quantum supremacy, which changed all the equations of quantum computation after that, and they have used this verification technique, and they have shown that yes, we have verified our computation for random circuits, and they have claimed that we have the supremacy of with quantum computation. Later on, IBM came up with their version of classical computation of that particular random circuit problem. But yeah, Google showed that yes, quantum supremacy can be achieved, and cross entropy benchmarking, this quantum verification is pretty much required. Otherwise, no one will give you a damn, because no one will trust you. So people are trusting their results because they have verified the results, right? So that is why quantum verification is very much required, because to show the supremacy, to show the advantage, you need to verify the results. And through verification, you can do benchmarking by estimating the noise and by implementing the larger computation, right? So these are the three terms, are very similar. They are interconnected, but they are different. The noise estimation is a different thing. Quantum verification is a different thing. And if you merge these two with the larger computational implementation, how far your quantum computer can go, you can do the benchmarking of a quantum hardware, right? Yeah. Okay. Is there any question till this slide? Because after that, I'm going to talk about our work that we have been doing for last 1 year. Yes. I have the last part remaining to describe. So is there any question regarding verification, noise estimation, or benchmarking? Any question? Otherwise, I'll shift to my work. Okay, I might complete my talk first, then maybe we can have a small discussion. Yes. So before going into the details of our work, I think I'm going to introduce one more topic here, which I have learned during my postdocs. I was not familiar with this term. I was not aware of this term, and that is measurement-based quantum computation. So all my life, like for 9+ years journey of my quantum computation, it was all about quantum circuit. I think everyone has talked about quantum circuit, quantum gates, qubits, and how you can prepare a circuit from algorithm for a particular computational problem. After arriving here in France, so I encountered with this measurement-based quantum computation, because many people from my group are working on measurement-based quantum computation, and it's a different kind of quantum computation. It is not similar to circuit model. Okay, uh, I have I have taken this slide from my collaborator, Professor Kashifi from Edinburgh and Sorbonne, and he tried to give a glimpse of this MBQC thing through circuit models, because many people can understand the circuit model very easily, right? That is why he tried to give an idea of this MBQC through circuit model. So in MBQC, you will have many qubits, and they, like you can see that they are correlated. That means you have some CG gate between them, and they are initialized with plus state, which means you have initialized with 0 followed by a Hadamard, and you have some input quantum state, and you are measuring the qubits in ZX basis, and through measurement you are doing the adaptive measurement. What does it mean by adaptive measurement? Adaptive measurement is like you are measuring one qubit, and based on the outcome of that qubit, you are adding some extra gate to other qubit, and again you are measuring, and through this plus and correlation, and through measurement or mixed circuit measurement, you are adapting the circuit in such a way so that you can perform the whole computation. Yes, I know it is really tough. It took me like 5 or 6 months to visualize this MBQC fully. Yes, but I really wanted to show you an overview of it, because beyond circuit, beyond this easy topics, there are many things, and I know that this you are starting in quantum computing. You need to understand more minutely the simple basic topics, but really I wanted to give you these ideas also, so that you are familiar with these terms also, so that if you are interested, you can come up to me after this talk through mail or LinkedIn, anywhere, and I'll be there. I promise that I'll be there for you. If you are interested, I'll be there for you to understand it very minutely, right? That is why I am including this thing. Yeah, so this is another way to describe the MBQC. You can see these are the qubits we have. These are the correlated gates, like CG gates, and you are like initializing all the qubits with plus state, right? And through this you can do MBQC, like you can measure the qubit, and based on the measurement results you need to correct the next qubit, right, based on the outcome. Through this you can do any computation, any circuit you have, any computation you have, you can do this measurement through this measurement based quantum computation also. But this is not similar to circuit type, because you need to do multiple number of measurements, you need to do multiple number, and you need to have that results, and based on that result you need to correct the next qubit also by using other Pauli gates, right? Another term I want to give you, that is blind quantum computation, which is discovered by the Professor Kashifi I mentioned earlier, and I took all this slide from her slides. And why blind quantum computation is required? Because if you think minutely, that I have told you that for verification, what is why verification is required? Because you need to check the correctness of your computation, right? You need to check the correctness of your computation. But if I tell you that your computation is already compromised, like a person who is verifying your computation is already know what type of computation you are trying to do, it is not secure, and they can like produce any result and they can say that yes, it is verified and it's correct and blah blah blah. So you need to do one thing. You need to secure your computation first, that whoever is verifying your computation doesn't know much about your computation. Otherwise, that fellow can predict the result, right? And you don't have any idea whether it is correct or not, or whether it is whether the verifier is doing right thing or not. So first of all, you need to secure your computation, and for that, blind quantum computation is one of the solver, right? What you can do, that you can do not only you are initializing with the plus operation, you are doing some extra angle theta also, so that you can rotate your initial state much a bit, and you know that you have rotated your initial state randomly through theta, and through that theta, that computation won't be visible to the verifier, right? Verifier cannot cannot extract the information much about your computation because of this blindness. Okay, so this blindness is important. That means whenever you are doing verification, you need two things, not the one thing. You need correctness. It is obvious. You need to prove that it is correct. And second thing is your computation need to be secured, right? It is need to be secured also. Here is an example or UBQC protocol which was designed by the University of Edinburgh pupil. They showed that if you have a MBQC model or this cluster states, we say that very often cluster states or graph states. This is an example of graph state of a MBQC model, and how you can verify one graph state, right? Here is a very good example. You have a target computation of this, right? And you have initialized with the blind quantum computation. That means verifier will not have much idea of your computation. You have already secured your computation. What you are trying to do now, you are trying to give some traps here, like you are providing your target computation, as well as you are giving some test computation also, where you are giving some traps here, which are like Clifford operation, which can be easily simulable through classically, right? Because you need to do verification through classical operation, right? So you are giving some trap operation here, and like these are your target computation, these are your trap operation, right? And this trap operation already been simulated classically in your computer, right? You know the outcome of this result. Now the verifier is, if giving the bad results of this particular trap rounds, then you can easily understand that this quantum computer is not giving the correct result, right? So I don't bother about the results of the target computation. What I am trying to do here is I have given some trap rounds also here, which can be classically simulable very easily. I know the answers. I'm giving all the circuit to the verifier, and verifier giving the results of it, and we are interested on the trap results. We are just comparing the results of trap rounds with our results or the estimated results, right? We are comparing them. If it is okay, then we are passing that yes, our computation are completely verified computations, right? It is giving the correct results, and it is also secure. It is also secure because we are giving the security thing, like blind quantum computation. So this is the quantum verification in MBQC. Now I'll talk about our work. I have, I think, less than 10 minutes. Maybe I can take, if I need, I can take 5 minutes more, right? I believe so. So let's talk about our work that we have been working. So we so what we are doing, first of all, you need to understand what we are doing. Our team is doing like verification, quantum verification for many years. Okay, quantum verification. What is quantum verification? You have a MBQC model, you have graph state, you are giving verifiers some trap circuit, right? And you know the results of these trap circuits, and the verifier giving the results of those circuits, and you are checking that the results of your trap circuit is similar to the results which have been given by the verifier or not, right? Now, now the question is, the verification is done. It is good. Now, how we can connect this verification in MBQC in benchmarking also, right? And not only benchmarking, we showed that through this verification, we can also estimate the noise of a quantum hardware or a quantum circuit, right? And for that, you need a computation first, right? And we took Q circuit computation, which is a BQP problem. BQP, I think you know already. Maybe someone has already told you. BQP is nothing but a bounded error quantum polynomial time. That means it's a polynomial time solvable problem with quantum computer, but with some bounded error. And this Q circuit is a deterministic problem, so it's very very easy to validate, because either it is giving yes or no, right? And it is BQP solvable, so it's a good point of case for our computation. What guarantee it is giving? It is giving the worst case scenario. Like yes, what happens? Like we are doing benchmarking, and it is giving the worst case scenario. How worst it can be, your computer, not the average thing you are getting. Right? That's a good thing. And what are the measures? Like every computational, you have already know that width and depth are the main thing for your matrix, right? How many qubits are required, how many depths are there. Well, next is hardware assumption. It's we need to repeat the process many times. Otherwise, if you don't sampling the method, you don't get enough probability outcome for your verification or for your benchmarking, right? But how many tests for a given guarantee? It's logarithmic. So you don't need exponential number of the test cases or rounds for your computation. So it's very fascinating that you required only logarithmic time of iteration or rounds to check for verification or for benchmarking. How many tests as the system size grows? That means scalability. I'm talking about scalability. Like you are having some computational problems, and it becomes exponentially large as compared to the previous computation. But you need some constant time of test cases, extra test cases to verify the computation or to benchmark your quantum hardware. So it's really, the results are very good, I must say. And like I have already mentioned this thing, that how could I check the efficiency and scalability, like in which benchmark is like, for that reason benchmark is working. We need to check the efficiency of your quantum hardware and the scalability of your quantum hardware. So we are taking some delta delta value, like threshold value, and we are saying that if our hardware is below this threshold, then our hardware is very sound, and this is efficient also if we need the logarithmic number of rounds also, right? And I have already talked about the scalability. Like if you grow the size of the computation very large, and we need some constant value of rounds, extra constant value of rounds, right? So, so this is the protocol we have designed for our benchmarking using verification, because we already know the verification protocol, right? That I have already gone through that verification. We are giving some track rounds, and we are checking and comparing, and through that we are having the result, right? So then I asked my professor, like I asked my postdoc supervisor, that how it can be useful. It can be, no, the question was like, we are getting so many information about trap rounds, right? Can we do one thing? Can we do something with this information? Like we are getting all the value of trap rounds, right? Can we do something with that? Because I was new to the field, I haven't much idea that what we can do. But with this particular question, my postdoc supervisor came up with two ideas. Like, yes, we can do two things. We can do benchmarking through this estimated results, because we are implementing so many computations, and we are just using them for verification. We are not using those information for any other cases, but we are saving those information in our Excel sheet or in our sheet, right? Now my postdoc supervisor said that we can use this information for benchmarking and noise estimation also. So it was very fascinating, right? So so we took those results, and we like and through those, and having those results, we tried to benchmark the quantum hardware. And for that reason, we have taken one delta value, one threshold value that should be given by the user as per the requirement, and we need to decide the number of rounds. In number of rounds, we need to decide that how many rounds we have to process this computation to have a good amount of value, so that we can benchmark a quantum computation, and define the size of the computation you want to test in terms of brick work state. Why brick work state? Because you know that circuit, right? You know the circuit of a computation. You have a computational problem, you have a quantum algorithm, you are designing, you are solving your computational problem through quantum algorithm, and you are having a quantum circuit, and you need to implement that quantum circuit, you will have the result. But in MBQC, you have to, you cannot deal with the circuit, right? The circuit needs to be converted in a brick work state, and brick work state look like this. So this is one kind of one of a kind graph states that that can be useful for a computation like Q circuit. Okay, so this is a brick work state, and for benchmarking, we need two type of variants of this brick work state. One is canonical, one is deviant, right? So we pick two type of round types, and this red defines the trap things, right? You remember the traps, right? So these are the actual computation, and these are the traps, and we use two type of traps round in our experiment. And maybe the circuit model would be helpful to understand. So this is kind of a small brick state of I think 8, yes, I think 7 number of it's 1 2 3 4 5 6, yeah, 7 number of qubits, where we showed that this is canonical and this is deviant one, and by changing the order of CG gate, we can have like two type of computation, right? And two type of trap rounds, and we have used that particular UBQC model, that particular trap round model for verification, and we are getting some information of those trap, right? Because we are implementing on a quantum hardware, and we are getting the result, and we are storing them in a sheet. And now we are checking that the failure ratio, right? How many of them are failed, and through that we are trying to benchmark. Like this, we have taken one computation, and we are benchmarking that computation based on the verification. And based on the result from the verification, we are trying to benchmarking that particular computation, that yes, this hardware can solve this Q circuit problem we have taken this 10% as a threshold, and it can be solved correctly and with security, and it can be verified easily, right? So through verification, we can benchmark this type of computational problem. There are many computational problem. We have many ideas on this. We are working on this. We'll come up different strategies, different computational problems for verification to benchmark the quantum hardware, right? So why does it work? Because it's estimating the noise. Because if trap fails, we know that it is because of the noise. So we have the idea of that estimation of noise, right? Not the estimation of noise. We have the idea of noise. Like the hardware is noisy. That is why it is failing, right? So through that we can implement a complete computation, and through that we can we have decided the number of rounds, we have decided the number of threshold, and we can benchmark that particular computation that it can be achievable on that particular quantum hardware, right? And also this is completely blind. This is completely secure protocol. Like other protocols are not very much secure. Anyone can be malicious. Anyone can be acted as a malicious thing, right? But this is completely secure protocol we wanted to give. And this is, I have already told you that it is efficient, it is scalable. I'm not going to repeat once again. And these are some simulation results where, like, we check for the global noise, we check for the local noise, like single or 2-qubit depolarizing noise. We check for them, and we like benchmark the Q circuit computation through verification, for further benchmarking, right? These are the results. I think I'm running out of time. I have only 2 slides left. I want to complete it in like 1 or 2 minutes. We didn't stop there. Like we had the results from verification. Through that results, we benchmarked the quantum computer. Then my professor, then my supervisor said that maybe you can look into noise estimation also. Then I started reading this noise estimation thing, and I came up with this ACES thing, right? And this ACES was very was working fine for the quantum circuits. Now I wanted to take that ACES for the MBQC graph states also. And as I mentioned, that we are having 2 type of traffified canonical and deviate form of this MBQC computation. And from that verification, you already know that you are getting all the probability of success or failure. And we need to, for ACES, I also told that you need to have multiple, like we need to sample your circuit multiple time or implement your circuit multiple times, so that you can have multiple number of linear equations. So through this verification, you are doing the same. You are sampling, you are implementing your graph state multiple of times, and from there you are getting all the linear equation, and solving those linear equation, we have like estimated the correlated and uncorrelated depolarizing noise, right? Depolarizing noise, I think it is already been covered in last 5 or 6 days. It's nothing but a XYZ Pauli errors, right? So we have shown that correlated and uncorrelated, both the depolarizing noise can be estimated through the result of this verification, right? And you can easily solve it through ACES, that average circuit eigenvalue sampling. So some results I want to show from our work, that it can be estimated. We took some 10 circuits, and the most fascinating part, it took only 5 seconds. So you can take more circuits, and it can easily estimate the noise through verification. So through verification, not only you can do benchmarking, you can do noise estimation also, right? So some results are given here. So finally, I want to conclude my talk. Maybe there are some future scope. First of all, maybe adaptive noise characterization. We need to have some real time techniques. Whatever I am saying, we need to do beforehand, right? But we need some real time techniques to dynamically monitor and adapt to noise changes, because noise are very time variant, right? With time, it changes. Like today, you are implementing something on a quantum hardware. Tomorrow, it's giving some results. Tomorrow, it will give different results. So real time monitoring is required for noise characterization, and it is pretty much required. Like hybrid verification protocols, combine classical and quantum resources. I'm talking about we need to have more verification protocols, because computation will be much larger, and we need some verification protocol. Yeah. So validate our larger quantum circuits. And lastly, universal
1 minute, I am
benchmarking.
interrupting you.
Yeah, yeah.
So, how long you need
This is the
to
last slide.
complete your
This is the
session,
last
sir?
slide. This is the last slide.
Okay, sir.
Yes. Yeah. And the last is the universal benchmarking, like you need one equation or something like that in which you can benchmark any available quantum hardware from any quantum technology. Yeah, that's all from my side. So I have given many new topic, many new titles, many new definitions. I know it's hard to understand this complex things in 90 minutes, and I believe that many people will come to me in future if you are interested to know more about these topics. Yeah, thank you for inviting me. Yes, any questions? I would love to give answers. I know I am
One
running out of
question,
time.
if you want.
So
Please,
one
one
thing,
question.
sir. Actually, we are running out of time. Our next
Yes.
session is will be started. It is to be started from 5.
Okay.
So
Yeah.
the speaker is waiting. So
Yeah.
is it possible to write the
Definitely.
question to the
Definitely.
participants are requested to raise your question
Always.
in writing? Sir will answer that. Or we can
Perfect.
take only one question in very short. Any question from the participant? Only one question. So I think participant will ask question to you in email.
Yeah.
I
They
think
can
so.
ask me offline. Yeah, they can ask me offline. I have given my email ID also here in the chat. Yeah.
So thank you, sir, for this wonderful and insightful session.
Yeah. Thank you.
I think participants have enjoyed the session, and if they have any queries, they will inform you
Definitely.
personally. Yeah.
Definitely. Thank you.
Thank you.
Bye-bye.
Thank you. Now, this is the end of session 12. Participants are requested to log in state link of session 13.